The old man will. The old man will.
Patent number 645,576. Nikola Tesla. Patented March 20th, 1900. System of transmission of electrical energy. Application filed September 2nd, 1897.
To all whom it may concern, be it known that I, Nikola Tesla, a citizen of the United States residing at New York, in the county and state of New York, have invented certain new and useful improvements in systems of transmission of electrical energy, of which the following is a specification, reference being had to the drawing, accompanying, and forming a part of the same. It has been well known heretofore that by rarefying the air enclosed in a vessel, its insulating properties are impaired to such an extent that it becomes what may be considered as a true conductor, although one of admittedly very high resistance. The practical information in this regard has been derived from observations necessarily limited in their scope by the character of the apparatus or means heretofore known, and the quality of the electrical effects producible thereby. Thus it has been shown by William Crookes in his classical researches, which have so far served as the chief source of knowledge of this subject, that all gases behave as excellent insulators until rarefied to a point corresponding to a barometric pressure of about 75 millimeters, and even at this very low pressure, the discharge of a high-tension induction coil passes through only a part of the attenuated gas in the form of a luminous thread, or R, a still further and considerable diminution of the pressure being required to render the entire mass of the gas enclosed in a vessel conducting. While this is true in every particular so long as electromotive or current impulses, such as are obtainable with ordinary forms of apparatus, are employed, I have found that neither the general behavior of the gases nor the known relations between electrical conductivity and barometric pressure are in conformity with these observations when impulses are used such as are producible by methods and apparatus devised by me, and which have peculiar and hitherto unobserved properties, and are of effective electromotive forces, measuring many hundred thousands or millions of volts. Through the continuous perfection of these methods and apparatus, and the investigation of the actions of these current impulses, I have been led to the discovery of certain highly important and useful facts, which have hitherto been unknown. Among these, and bearing directly upon the subject of my present application, are the following. First, that atmospheric or other gases, even under normal pressure, when they are known to behave as perfect insulators, are in a large measure deprived of their dielectric properties by being subjected to the influence of electromotive impulses of the character and magnitude I have referred to, and assume conducting and other qualities which have been so far observed only in gases greatly attenuated or heated to a high temperature, and second, that the conductivity imparted to the air or gases increases very rapidly, both with the augmentation of the applied electrical pressure and with the degree of rarefaction, the law, in this latter respect, being, however, quite different from that heretofore established. In illustration of these facts, a few observations which I have made with apparatus devised for the purposes here contemplated may be cited. For example, a conductor or terminal, to which impulses, such as those here considered, are supplied, but which is otherwise insulated in space and is remote from any conducting bodies, is surrounded by a luminous flame-like brush, or discharge, often covering many hundreds, or even as much as several thousands of square feet of surface. This striking phenomenon clearly testing the high degree of conductivity which the atmosphere attains under the influence of the immense electrical stresses to which it is subjected. This influence is, however, not confined to that portion of the atmosphere which is discernible by the eye as luminous, and which, as has been the case in some instances actually observed, may fill the space within a spherical or cylindrical envelope of a diameter of 60 feet or more, but reaches out to far remote regions, the insulating qualities of the air being, as I have ascertained, still sensibly impaired at a distance many hundred times that through which the luminous discharge projects from the terminal, and in all probability much farther. The distance extends with the increase of the electromotive force of the impulses, with the diminution of the density of the atmosphere, with the elevation of the active terminal above the ground, and also, apparently, in a slight measure, with the degree of moisture contained in the air. I have likewise observed that this region of decidedly noticeable influence continuously enlarges as time goes on, and the discharge is allowed to pass not unlike a conflagration which slowly spreads, this being possibly due to the gradual electrification or ionization of the air, or to the formation of less insulating gaseous compounds. It is, furthermore, a fact that such discharges of extreme tensions, approximating those of lightning, manifest a marked tendency to pass upward away from the ground, which may be due to electrostatic repulsion, or possibly to slight heating and consequent rising of the electrified or ionized air. These latter observations make it appear probable that a discharge of this character, allowed to escape into the atmosphere from a terminal maintained at a great height, will gradually leak through and establish a good conducting path to more elevated and better conducting air strata, a process which possibly takes place in silent lightning discharges frequently witnessed on hot and sultry days. It will be apparent to what an extent the conductivity imparted to the air is enhanced by the increase of the electromotive force of the impulses, when it is stated that in some instances the area covered by the flame discharge mentioned was enlarged more than sixfold by an augmentation of the electrical pressure, amounting scarcely to more than 50%. As to the influence of rarefaction upon the electric conductivity imparted to the gases, it is noteworthy that, whereas the atmospheric or other gases begin ordinarily to manifest this quality at something like 75 millimeters barometric pressure, with the impulses of excessive electromotive force to which I have referred, the conductivity, as already pointed out, begins even at normal pressure and continuously increases with the degree of tenuity of the gas, so that at, say, 130 millimeters pressure, when the gases are known to be still nearly perfect insulators for ordinary electromotive forces, they behave toward electromotive impulses of several millions of volts like excellent conductors, as though they were rarefied to a much higher degree. By the discovery of these facts and the perfection of means for producing in a safe, economical, and thoroughly practicable manner current impulses of the character described, it becomes possible to transmit through easily accessible and only moderately rarefied strata of the atmosphere electrical energy, not merely in insignificant quantities, such as are suitable for the operation of delicate instruments and like purposes, but also in quantities suitable for industrial uses on a large scale, up to practically any amount, and according to all the experimental evidence I have obtained, to any terrestrial distance. To conduce to a better understanding of this method of transmission of energy, and to distinguish it clearly, both in its theoretical aspect and in its practical bearing, from other known modes of transmission, it is useful to state that all previous efforts, made by myself and others, for transmitting electrical energy to a distance without the use of metallic conductors, chiefly with the object of actuating sensitive receivers, have been based, insofar as the atmosphere is concerned, upon those qualities which it possesses by virtue of its being an excellent insulator, and all these attempts would have been obviously recognized as ineffective, if not entirely futile, in the presence of a conducting atmosphere or medium. The utilization of any conducting properties of the air for purposes of transmission of energy has been hitherto out of the question in the absence of apparatus suitable for meeting the many and difficult requirements, although it has long been known or surmised that atmospheric strata at great altitude, say 15 or more miles above sea level, are, or should be, in a measure, conducting. But assuming even that the indispensable means should have been produced, then still a difficulty, which in the present state of the mechanical arts must be considered as insuperable, would remain, namely, that of maintaining terminals at elevations of 15 miles or more above the level of the sea. Through my discoveries before mentioned, and the production of adequate means, the necessity of maintaining terminals at such inaccessible altitudes is obviated, and a practical method and system of transmission of energy through the natural media is afforded essentially different from all those available up to the present time, and possessing, moreover, this important practical advantage, that whereas in all such methods or systems heretofore used or proposed, but a minute fraction of the total energy expended by the generator or transmitter was recoverable in a distant receiving apparatus by my method and appliances, it is possible to utilize by far the greater portion of the energy of the source, and in any locality, however remote from the same. Expressed briefly, my present invention, based upon these discoveries, consists then in producing at one point an electrical pressure of such character and magnitude as to cause thereby a current to traverse elevated strata of the air between the point of generation and a distant point at which the energy is to be received and utilized. In the accompanying drawing, a general arrangement of apparatus is diagrammatically illustrated, such as I contemplate employing in the carrying out of my invention on an industrial scale, as, for instance, for lighting distant cities or districts from places where cheap power is obtainable. Referring to the drawing, A is a coil, generally of many turns and of a very large diameter, wound in spiral form either about a magnetic core or not, as may be found necessary. C is a second coil, formed of a conductor of much larger section and smaller length, wound around and in proximity to the coil. A. In the transmitting apparatus, the coil A constitutes the high-tension secondary, and the coil C the primary of much lower tension of a transformer. In the circuit of the primary, C is included a suitable source of current, G. One terminal of the secondary A is at the center of the spiral coil, and from this terminal the current is led by a conductor B to a terminal D, preferably of large surface, formed or maintained by such means as a balloon at an elevation suitable for the purposes of transmission, as before described. The other terminal of the secondary A is connected to earth, and, if desired, also to the primary, in order that the latter may be at substantially the same potential as the adjacent portions of the secondary, thus ensuring safety. At the receiving station, a transformer of similar construction is employed, but in this case the coil A, of relatively thin wire, constitutes the primary, and the coil C, of thick wire or cable, the secondary of the transformer. In the circuit of the latter are included lamps L, motors M, or other devices for utilizing the current. The elevated terminal D is connected with the center of the coil A, and the other terminal of said coil is connected to earth, and preferably, also, to the coil C, for the reasons above stated. It will be observed that in coils of the character described, the potential gradually increases with the number of turns toward the center, and the difference of potential between the adjacent turns being comparatively small, a very high potential, impracticable with ordinary coils, may be successfully obtained. It will be, furthermore, noted that no matter to what an extent the coils or may be modified in design and construction, owing to their general arrangement and manner of connection. As illustrated, those portions of the wire or apparatus which are highly charged will be out of reach, while those parts of the same which are liable to be approached, touched, or handled will be at or nearly the same potential as the adjacent portions of the ground, this ensuring, both in the transmitting and receiving apparatus, and regardless of the magnitude of the electrical pressure used, perfect personal safety, which is best evidenced by the fact that although such extreme pressures of many millions of volts have been for a number of years continuously experimented with no injury, has been sustained neither by myself or any of my assistants. The length of the thin wire coil in each transformer should be approximately 1/4 of the wavelength of the electric disturbance in the circuit, this estimate being based on the velocity of propagation of the disturbance through the coil itself and the circuit with which it is designed to be used. By way of illustration, if the rate at which the current traverses the circuit, including the coil, be 185,000 miles per second, then a frequency of 925 per second would maintain 925 stationary waves in a circuit 185,000 miles long, and each wave would be 200 miles in length. For such a low frequency, to which I shall resort only when it is indispensable to operate motors of the ordinary kind under the conditions above assumed, I would use a secondary of 50 miles in length. By such an adjustment, or proportioning of the length of wire in the secondary coil or coils, the points of highest potential are made to coincide with the elevated terminals DD, and it should be understood that whatever length be given to the wires, this condition should be complied with in order to attain the best results. As the main requirement in carrying out my invention is to produce currents of an excessively high potential, this object will be facilitated by using a primary current of very considerable frequency, since the electromotive force obtainable with a given length of conductor is proportionate to the frequency. But the frequency of the current is in a large measure arbitrary, for if the potential be sufficiently high, and if the terminals of the coils be maintained at the proper altitudes, the action described will take place, and a current will be transmitted through the elevated air strata, which will encounter little and possibly even less resistance than if conveyed through a copper wire of a practicable size. Accordingly, the construction of the apparatus may be in many details greatly varied, but in order to enable any person skilled in the mechanical and electrical arts to utilize to advantage in the practical applications of my system, the experience I have so far gained the following particulars of a model plant, which has been long in use, and which was constructed for the purpose of obtaining. Further data to be used in the carrying out of my invention on a large scale are given. The transmitting apparatus was in this case one of my electrical oscillators, which are transformers of a special type, now well known and characterized by the passage of oscillatory discharges of a condenser through the primary. The source, G, forming one of the elements of the transmitter, was a condenser of a capacity of about 4/100ths of a microfarad, and was charged from a generator of alternating currents of 50,000 volts pressure, and discharged by means of a mechanically operated brake 5,000 times per second through the primary C. The latter consisted of a single turn of stout, stranded cable of inappreciable resistance and of an inductance of about 8,000 centimeters, the diameter of the loop being very nearly 244 centimeters. The total inductance of the primary circuit was approximately 10,000 centimeters, so that the primary circuit vibrated generally, according to adjustment, from 230,000 to 250,000 times per second. The high-tension coil A, in the form of a flat spiral, was composed of 50 turns of heavily insulated cable, numbered at 8 wound in one single layer, the turns beginning close to the primary loop and ending near its center. The outer end of the secondary or high-tension coil A was connected to the ground, as illustrated, while the free end was led to a terminal placed in the rarefied air stratum through which the energy was to be transmitted, which was contained in an insulating tube of a length of 50 feet or more, within which a barometric pressure varying from about 120 to 150 millimeters was maintained by means of a mechanical suction pump. The receiving transformer was similarly proportioned, the ratio of conversion being the reciprocal of that of the transmitter, and the primary high-tension coil A was connected, as illustrated, with the end near the low-tension coil C to the ground, and with the free end to a wire or plate, likewise placed in the rarefied air stratum, and at the distance named from the transmitting terminal. The primary and secondary circuits in the transmitting apparatus being carefully synchronized, an electromotive force from 2 to 4 million volts and more was obtainable at the terminals of the secondary coil A. The discharge passing freely through the attenuated air stratum maintained at the above barometric pressures, and it was easy under these conditions to transmit with fair economy considerable amounts of energy, such as are of industrial moment, to the receiving apparatus for supplying from the secondary coil C-lamps L or kindred devices. The results were particularly satisfactory when the primary coil or system A, with its secondary C, was carefully adjusted so as to vibrate in synchronism with the transmitting coil or system AC. I have, however, found no difficulty in producing with apparatus of substantially the same design and construction electromotive forces exceeding 3 or 4 times those before mentioned, and have ascertained that by their means current impulses can be transmitted through much denser air strata. By the use of these, I have also found it practicable to transmit notable amounts of energy through air strata not in direct contact with the transmitting and receiving terminals, but remote from them, the action of the impulses in rendering conducting air of a density at which it normally behaves as an insulator, extending, as before remarked, to a considerable distance. The high electromotive force obtained at the terminals of coil or conductor A was, as will be seen in the preceding instance, not so much due to a large ratio of transformation as to the joint effect of the capacities and inductances in the synchronized circuits, which effect is enhanced by a high frequency, and it will be obviously understood that if the latter be reduced, a greater ratio of transformation should be resorted to, especially in cases in which it may be deemed of advantage to suppress as much as possible, and particularly in the transmitting coil A, the rise of pressure due to the above effect, and to obtain the necessary electromotive force solely by a large transformation ratio. While electromotive forces, such as are produced by the apparatus just described, may be sufficient for many purposes to which my system will or may be applied, I wish to state that I contemplate using, in an industrial undertaking of this kind, forces greatly in excess of these, and with my present knowledge and experience in this novel field, I would estimate them to range from 20 to 50 million volts, and possibly more. By the use of these much greater forces, larger amounts of energy may be conveyed through the atmosphere to remote places or regions, and the distance of transmission may be thus extended practically without limit. As to the elevation of the terminals DD, it is obvious that it will be determined by a number of things, as by the amount and quality of the work to be performed, by the local density and other conditions of the atmosphere, by the character of the surrounding country, and such considerations as may present themselves in individual instances. Thus, if there be high mountains in the vicinity, the terminals should be at a greater height, and generally they should always be, if practicable, at altitudes much greater than those of the highest objects near them, in order to avoid as much as possible the loss by leakage. In some cases, when small amounts of energy are required, the high elevation of the terminals, and more particularly of the receiving terminal D, may not be necessary, since especially when the frequency of the currents is very high, a sufficient amount of energy may be collected at that terminal by electrostatic induction from the upper air strata, which are rendered conducting by the active terminal of the transmitter, or through which the currents from the same are conveyed. With reference to the facts which have been pointed out above, it will be seen that the altitudes required for the transmission of considerable amounts of electrical energy in accordance with this method are such as are easily accessible and at which terminals can be safely maintained, as by the aid of captive balloons supplied continuously with gas from reservoirs and held in position securely by steel wires, or by any other means, devices, or expedients, such as may be contrived and perfected by ingenious and skilled engineers. From my experiments and observations, I conclude that with electromotive impulses, not greatly exceeding 15 or 20 million volts, the energy of many thousands of horsepower may be transmitted over vast distances, measured by many hundreds and even thousands of miles, with terminals not more than 30 to 35,000 feet above the level of the sea, and even this comparatively small elevation will be required chiefly for reasons of economy, and, if desired, it may be considerably reduced, since by such means as have been described, practically any potential that is desired may be obtained. The currents through the air strata may be rendered very small, whereby the loss in the transmission may be reduced. It will be understood that the transmitting as well as the receiving coils, transformers, or other apparatus may be in some cases movable, as for example, when they are carried by vessels floating in the air or by ships at sea. In such a case, or generally, the connection of one of the terminals of the high-tension coil or coils to the ground may not be permanent, but may be intermittently or inductively established, and any such or similar modifications I shall consider as within the scope of my invention. While the description here given contemplates chiefly a method and system of energy transmission to a distance through the natural media for industrial purposes, the principles which I have herein disclosed, and the apparatus which I have shown, will obviously have many other valuable uses, as, for instance, when it is desired to transmit intelligible messages to great distances, or to illuminate upper strata of the air, or to produce, designedly, any useful changes in the condition of the atmosphere, or to manufacture from the gases of the same products, as nitric acid, fertilizing compounds, or the like, by the action of such current impulses, for all of which and for many other valuable purposes they are eminently suitable, and I do not wish to limit myself in this respect. Obviously also, certain features of my invention here disclosed will be useful as disconnected from the method itself, as for example, in other systems of energy transmission, for whatever purpose they may be intended, the transmitting and receiving transformers arranged and connected, as illustrated, the feature of a transmitting and receiving coil or conductor, both connected to the ground and to an elevated terminal and adjusted so as to vibrate in synchronism, the proportioning of such conductors or coils, as above specified, the feature of a receiving transformer with its primary connected to earth and to an elevated terminal, and having the operative devices in its secondary and other features or particulars, such as have been described in this specification or will readily suggest themselves by a perusal of the same. I do not claim in this application a transformer for developing or converting currents of high potential in the form herewith shown and described, and with the two coils connected together, as and for the purpose set forth. having made these improvements, the subject of a patent granted to me, November 2, 1897, Num 593, 138, nor do I claim herein the apparatus employed in carrying out the method of this application when such apparatus is specially constructed and arranged for securing the particular objects sought in the present invention, as these last-named features are made the subject of an application filed as a division of this application on February 19, 1900, serial number 5780. What I now claim is 1. The method herein before described of transmitting electrical energy through the natural media, which consists in producing, at a generating station, a very high electrical pressure, causing thereby a propagation or flow of electrical energy by conduction through the earth and the air strata, and collecting or receiving, at a distant point, the electrical energy so propagated or caused to flow. 2. The method herein before described of transmitting electrical energy, which consists in producing at a generating station a very high electrical pressure, conducting the current caused thereby to earth and to a terminal at an elevation at which the atmosphere serves as a conductor therefore, and collecting the current by a second elevated terminal at a distance from the first. 3. The method herein before described of transmitting electrical energy through the natural media, which consists in producing between the earth and a generator terminal elevated above the same, at a generating station, a sufficiently high electromotive force to render elevated air strata conducting, causing thereby a propagation or flow of electrical energy by conduction through the air strata, and collecting or receiving at a point distant from the generating station the electrical energy so propagated or caused to flow. 4. The method herein before described of transmitting electrical energy through the natural media, which consists in producing between the earth and a generator terminal elevated above the same, at a generating station, a sufficiently high electromotive force to render the air strata at or near the elevated terminal conducting, causing thereby a propagation or flow of electrical energy by conduction through the air strata, and collecting or receiving at a point distant from the generating station the electrical energy so propagated or caused to flow. 5. The method herein before described of transmitting electrical energy through the natural media, which consists in producing between the earth and a generator terminal elevated above the same, at a generating station, electrical impulses of a sufficiently high electromotive force to render elevated air strata conducting, causing thereby current impulses to pass, by conduction, through the air strata, and collecting or receiving at a point distant from the generating station the energy of the current impulses by means of a circuit synchronized with the impulses. G. The method herein before described of transmitting electrical energy through the natural media, which consists in producing between the earth and a generator terminal elevated above the same, at a generating station, electrical impulses of a sufficiently high electromotive force to render the air strata at or near the elevated terminal conducting, causing thereby current impulses to pass through the air strata, and collecting or receiving at a point distant from the generating station the energy of the current impulses by means of a circuit synchronized with the impulses. 7. The method herein before described of transmitting electrical energy through the natural media, which consists in producing between the earth and a generator terminal elevated above the same, at a generating station, electrical impulses of a wavelength so related to the length of the generating circuit or conductor as to produce the maximum potential at the elevated terminal, and of sufficiently high electromotive force to render elevated air strata conducting, causing thereby a propagation of electrical impulses through the air strata, and collecting or receiving at a point distant from the generating station, the energy of such impulses by means of a receiving circuit having a length of conductor similarly related to the wavelength of the impulses. 8. The method herein before described of transmitting electrical energy through the natural media, which consists in producing, between the earth and a generator terminal elevated above the same, at a generating station, a sufficiently high electromotive force to render elevated air strata conducting, causing thereby a propagation or flow of electrical energy through the air strata by conduction, collecting or receiving the energy so transmitted by means of a receiving circuit at a point distant from the generating station, using the receiving circuit to energize a secondary circuit, and operating translating devices by means of the energy so obtained in the secondary circuit. 9. The method herein before described of transmitting electrical energy through the natural media, which consists in generating current impulses of relatively low electromotive force at a generating station, utilizing such impulses to energize the primary of a transformer, generating by means of such primary circuit impulses in a secondary surrounding by the primary and connected to the earth and to an elevated terminal of sufficiently high electromotive force to render elevated air strata conducting, causing there by impulses to be propagated through the air strata, collecting or receiving the energy of such impulses at a point distant from the generating station, by means of a receiving circuit connected to the earth and to an elevated terminal, and utilizing the energy so received to energize a secondary circuit of low potential surrounding the receiving circuit.
Witnesses: Nikola Tesla, M. Lawson Dyer, G.W. Martling.
I wanted to thank everybody for watching today. If you like this kind of content, we do a live show every Monday, Wednesday, and Friday right here on YouTube, 2 p.m. Pacific Standard Time on the main channel. The link will be in the description. Please join us, get in the chat, and have some fun. With all that said, hit the music.
The old man will. The old man will. The old man will. The old man builds.
The old man builds is broken in the head. People not seeing reality has put them in the red. Where conscious and spirituality been stricken from the norm and replaced with the ignorance of basic magnetic form. The geometry of God keeps running through his head. That's what makes old man builds broken in the head. The old man builds. The old man builds. Spheres of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to instead. The old man builds.